Okay, so now it's recording, and good morning, everyone, and welcome to lecture 9 of the Quantum Theory in a Nutshell course. So, yesterday we were discussing about polarization of light, and in particular, we had a discussion on how to describe polarization in terms of electric fields. So considering light as an electromagnetic wave. And then we wanted to describe the same physical phenomenon, but now treating light as a beam of photons. And this immediately led to the conclusion that what you compute when you treat light as a beam of photons is the probability for a photon with a given polarization to cross a polarizer. Okay, so we started the discussion by treating light as an electromagnetic wave, and we have seen that if you place two polarizers, one after the other, the intensity of light after the first polarizer with polarization theta is given by I naught, and the intensity of light after the second polarizer with polarization phi is given by I, and I and I naught are related by this expression here. So they are related by this cosine squared of the difference between the two angles. And we were speaking about linear polarization. So our polarizers, they have the mission of filtering the electric field just in one direction. So after the polarizer, the electric field that forms the electromagnetic wave will oscillate in a particular direction. So I received an email with a question by Eva. I hope I'm pronouncing the name correctly. If not, let me know. And the question was how, okay, good. So what is the relation of this with quantum mechanics? And so in principle, if you just take this description of radiation as being just an electric magnetic wave, then you can perfectly describe the polarization as a way of selecting one particular component of the electric field, and the electric field will be oscillating in this direction. However, as we have seen, light can be described also in terms of photons, and we want to describe the same polarization phenomenon now in the language of photons. And the relation with quantum mechanics is that the language that we are introducing now in order to describe polarization of light as a beam of photons is the language of quantum mechanics. So we are learning how to describe a quantum state of a photon in a given polarization, and we are learning how to compute the probability of getting a photon with polarization phi if the photons that were sent against the polarizer are polarized in the direction theta. So we are introducing these concepts that are, I mean, the core of quantum mechanics. So in quantum mechanics, if you want to measure a quantity, typically you don't get the same result if you make successive measurements of the quantity. What I mean by that, you prepare the system and you want to measure one particular physical quantity about the system. So you prepare the system, you make the measurement, you get a value. You prepare the same system under the same conditions, and you make another measurement of the same physical quantity, and you can get a different value. So what we can predict in quantum mechanics is the probability that you're going to get a given value for a physical quantity. And this is what we are discussing here, because we are formulating the polarization of light as the question, what is the probability that a photon that was prepared with polarization theta is going to pass through a polarizer with polarization phi? And this is given by the cosine squared of the difference between the angles. Okay, so I hope this helps in the clarification of the question. If not, let me know. Okay, so we have discussed this this fact. You're welcome, about the probability of getting photons in a given with a given polarization after being prepared in other polarization. And what we started doing yesterday was to observe that actually I could rewrite not the probability, but a part of the probability, namely, so the probability is cosine squared, but I can write cosine of theta minus phi using this trigonometric identity. So I can separate as cosines and sines of the angles. And finally, the sum can be rearranged as a product between two vectors. So I have a vector that just gives information about the polarization in the direction theta, and I have another vector that gives information about the polarization phi. So what we were discussing was that if I have a photon with polarization theta, I will describe it with this vector, this column vector, that I call the state vector associated to the photon in polarization theta. Okay, and I wrote down a definition of what a state vector is, and for the moment I'm restricting the definition to vectors with two entries. But as we discussed, I mean, we can have vectors with more entries, and in particular we can have vectors with infinitely many entries. Okay, but since this state vector will be used in the future to compute probabilities, I am demanding that this vector has norm equals to 1. So if I compute the absolute value of the first entry and square it and sum with the square of the absolute value of the second entry, this sum must give 1. We are going to understand this a bit better today. Also, I mentioned that in principle, so this is not the case here, cosine and sine are real functions, but I said that in principle, C1 and C2 in a generic state vector can be complex numbers. So you have to be careful about that, because when I mean take the absolute value here, for real numbers, this essentially means that you take the number, and if it is positive, it stays the same, and if it is negative, you flip the sign. But if this is a complex number, then the absolute value, or what I mean by absolute value in the case of complex numbers is to take the square. So I'm going to get there, so I don't want to, but just to remember you that complex numbers, they have real part and imaginary part. So you have to square those quantities and take the square root if you want to take the absolute value of a complex number. But I'm going to refresh your minds about that in a second. So we introduced a notation to represent this state vector in polarization theta. So if a photon is polarized in the direction theta, then I will assign to it this column vector, and I will call this as this this name here. So I'm labeling this vector with this notation here, and as we have discussed, this is called a ket. And so this is a Dirac notation for a state vector, and this is represented by a ket. And now if you want to describe a row vector, so a row vector is a different mathematical structure than a column vector. Instead of writing this notation of ket, we introduce this notation that we call bra. So when I write this cusp here on the left-hand side of the name of the vector, then I mean a row vector. When I write this cusp on the right-hand side, I mean a column vector. And now I can take the product of these two vectors. So if I take the product between a row vector with a column vector, then I'll get a scalar. So this is a scalar product, and the notation for that is given by this representation here, which is the well-known Dirac bracket notation. Okay? So if you take this row vector multiplied by this column vector, you get these two numbers multiplying these two numbers and being summed. And you go back to this expression here, which is nothing but cosine of theta minus phi. Okay? So the scalar product between this row vector and this column vector is giving cosine of theta minus phi. Okay? But we have seen that the probability of getting a photon with polarization phi, if it was prepared with polarization theta, is actually cosine squared. So what we do, we can just square this equation, and this will be cosine squared, and this will be the Dirac bracket squared. Okay? So since, as I mentioned, this can be a complex number, in principle, if the state vector is a complex vector, this quantity can be a complex number. And since this is being assigned to a probability, and probability is a real thing, then I better take the absolute value here. So I take the absolute value and square it. So what I'm saying here is that the probability of getting a photon with polarization phi, if it is prepared in a quantum state with polarization theta, is the absolute value of the Dirac bracket, namely the scalar product between these two quantities, is squared. Okay? So you go back, you take this product between this row vector, this column vector, you obtain this expression, you use this trigonometric identity and reduce this to this, and you square that. So, and this is the probability that we have learned yesterday. Okay, so I see that there is something in the chat. Let me check. Is there a relation between the first quantum state and Bryan-Ket states? I'm not sure if I understood the question, Mahmoud. Can you elaborate a bit more?
Yes, hello.
Hi.
I mean, is it necessary to take the first quantum state and represent it as Ket state and the final or the second quantum state at Bra?
Okay, that's I understood now. That's a good question, actually. So you see that when I explained this experiment here, there was an order, right? So first I prepared the state of the photon to be polarized with polarization theta. And then I passed it through the polarizer with polarization phi. So you see that there is a state that enters that will pass through the polarizer, and there is a state that will be the final state of the experiment. So I'm asking that, given that the state was prepared with polarization theta, what is the probability of finding it with polarization phi? Okay, so you see that theta comes first in the experiment and phi comes after. So there is this, how can I say? There is this order in this experiment where first I have a state vector theta, and in the end I have a state vector which is phi. So if I want to, and in order to represent that, we say that we want to compute the probability that a photon that is prepared in the state theta is found in the state phi. So in this sense, there is this order. But as we discussed yesterday, this is, if the vectors are real, you can just exchange the order here, and this will not change the value that you get here, right? So, but if the vectors are complex, then you change the result. But since the probability is just the absolute value squared, this will not change the probability. So in the end, it doesn't matter too much if you exchange the order at the level of probabilities, okay? But this is a probability amplitude, right? So you have to take the absolute value and the square. And at this level, if the vectors are complex, then the result will change. Okay, yeah. Mahmoud, okay, because your microphone is on, so I thought you were going to say something. Okay. Okay. But as I said, we will deal with state vectors that have entries that are complex numbers. So we have to be a bit more careful when we deal with these state vectors that have these entries as complex numbers. So if you define a state vector C, and the entries are C1 and C2, and these are complex numbers, then when you define the bra associated with this ket, so let me remind you that if you have a ket, you can obtain the bra in the real case just by taking the transpose of this vector. This will give you a row vector with entries C1 and C2. Okay, so if I take this vector here, this ket theta, and I take the transpose of this vector, then I'll get a row vector with entries cosine and sine, and this is the bra associated with theta that I would call simply this, right? However, when the vectors are complex, you have to do an extra operation. So if you want to compute the bra associated with this ket, you have to transpose the vector. So you're going to turn this into a row vector, but then you have to take the complex conjugate of each entry, okay? So C1 will be mapped to C1 star, and C2 will be mapped to C2 star. So this is the bra associated with this ket. And this is very important. I mean, you see that C1 and C2, they belong to the complex numbers. So if you want to compute the the bra associated with this cat, you transpose and take the complex conjugate. Well, you can take this as a general rule because, of course, if you take the complex conjugate of real numbers, this is the same as the real number itself. So here you can say that when I take the bra associated with theta, what I'm actually doing is to compute cosine and star sine of theta star. But of course, cosine star is cosine and sine star is sine. So this is not going to change. Okay, so someone, let me check the. So, okay, you call that dual, is that right? Yes. So we often say that the bra is the dual uh, to the cat. And by dual, I mean that if I multiply a bra with a cat, I get a scalar. So the dual is the representation that when I multiply this with the cat, I get a scalar. And this is so in a abstract representation of the state vectors. So here we are dealing with two with column vectors with two entries. So it's something very concrete, and we know how to find the dual very easily. But for generic vector states, which are much more involved than a simply two entries vector, the bra actually is a linear function that associates with the cat a scalar number. Sorry, yes, a scalar. Yeah. So this is a vector. This lives in the vector space, and this is a linear function that maps an element of your vector space into a scalar. So this is, you see that I'm introducing more a mathematical language that is more sophisticated than what I'm saying about this simple system. But I don't want to, let's say, spend like a lot of time with the mathematical properties and go deep in the math, because I think quantum mechanics is the type of subject that you must start with the easy thing, and then you start putting the cherries on top of that, because otherwise it can get really complicated. Okay. Okay, good. So now if I want to compute the Dirac bracket between two vectors, between two state vectors, A and B, remember, I have to take, let's assume that I want to compute that. I take B. B has two entries, B1 and B2, and this is the cat B. So I have the column vector, and I have the bra A. And let's assume that the cat A has entries A1 and A2. So if I want to compute the bra associated with A, I have to transpose and take the complex conjugate. Okay? The complex conjugate of A1 is A1 star, of A2 is A2 star, and then I have to perform this product. And when I perform this product, then I will get A1 star times B1 plus A2 star times B2, and I get this result here. Again, this is a number, okay? But you see that now I have stars on the A's and I don't have stars on the B's. So this means that if I compute the scalar product or the Dirac bracket between B and A, now the stars will be on top of B and not on top of A. So I get B1 star, A1, plus B2 star, A2. So this answer here, this number here, is not the same as this number in general, right? So actually, this number here is the complex conjugate of this number. So what I'm concluding is that BA is the same as AB star. So then, Mahmoud, now you see that uh, um, if I exchange the orders, I get a number which is the complex conjugate of the first number. Okay. But of course, if I want to compute probabilities, I have to take the absolute value and square. But two complex numbers that are, one is the complex conjugate of the other, they have the same absolute value. So the probability will not change if I compute BA or AB, but the amplitude will change. Okay. So I was thinking that it is useful for us to make a short recap about complex numbers, because in the first day I gave you a form to fill in, and some of you said that I mean, you are not too familiar with complex number algebra. So if you are, then this will be useful for us to just fix the notation and make sure that we use the same language for the properties of complex numbers. And if you are not, I don't think this recap will make you an expert on complex numbers. At least you're going to see the main properties that we are going to need, okay? So let me just make this brief recap about complex numbers. So a complex number Z, I say that Z belongs to the complex number set, is defined as, so it has this structure here. Z is written as A plus IB, where A and B belong to the real numbers set, and I is a number that is a new number, is a new quantity that has this property: I squared is -1. So we often denote I as being the square root of -1. Okay. So this is something that it's not allowed in the set of real numbers, but we extend that to the complex numbers by introducing this new element, which is the imaginary well, some people call the imaginary unit and so on, but this is just, you just think of I as being a number that you can square, and this gives -1. Okay. So a real number has this structure. I have so a complex number has this structure. I have a real number plus I times another real number. So there is a question in the chat. Let me see. Is there physical meaning when we change the state? So you see that when you have a cat and when you have a bra, you are talking about mathematical entities that describe a physical system. So if you have a cat, you automatically have a bra associated to it. So it's not like you're changing from one to the other. It's just that if you have one state vector, you can define the dual. Okay, and as we're going to see, we have to be able to perform mathematical operations with these two quantities. So sometimes you describe a system with a given state vector, which is a cat, but we're going to need to compute the bra of this associated with this cat. But I think this will become clear soon, why you need to have these two quantities. You're welcome. Okay, so now we define what I was speaking about before, what is known as the complex conjugate of z. So if you have a complex number z, I can take its complex conjugate, and this is denoted by z star. So z star is the complex conjugate of z, and this is defined by the following property. So if z is a plus ib, then z star is by definition a minus ib. So you change the sign of the part that comes with I. This is what we call the complex conjugate. And the complex conjugate has another property, which is if I take the complex conjugate now of z star, so I have z star, and I want to ask you, what is the complex conjugate of z star? So you have to see the number here and change the sign of the part that comes with I. So this will be A plus IB, which is nothing but Z. Okay? So if you take Z, take the complex conjugate, you get this. And if you take another time the complex conjugate, you get back to Z. Okay? So we introduce some notation here. The number A, which is the number that comes free of the I, is what we call the real part of the complex number Z. And we denote that by this notation here. This is the real part of Z. So if I ask what is the real part of Z, this will be A. Okay? Now there is this real number that multiplies I, and this is called the imaginary part of Z. Okay? And we denote that by imaginary Im of Z. Okay? So if I ask you what is the imaginary part of Z, the answer is B. If I ask you what is the imaginary part of Z star, then it is minus B, because this is what multiplies I. Also, if I ask what is the real part of Z star, this is just A. Okay? So you see that complex conjugate numbers, they have the same real part, but the imaginary part is such that they have opposite signs. Okay? This is another way of defining the complex conjugate. And we say that a number Z is real if it is equal to its complex conjugate, right? So if you have a real number, then by definition, B must be 0. And then if you take the complex conjugate of a number that has B equals to 0, this is simply the same number. So the complex conjugate, when you take a number, you take the complex conjugate of this number, and this is the same number as before, then this is a real number. Okay? Okay, good. And now we can define the following. So if we have a complex number W with entries with real part W1 and imaginary part W2, I can compute the product of W with W star. Okay? This is the same, of course, as W star W. So if I can commute these numbers. And if you work out the explicit expression of this will be the absolute value of W1 squared plus the absolute value of W2 squared. So if you take W times W star, this will be a real number. Okay, but see, I am computing the product of a complex number with its complex conjugate. And this is a real number. Okay? It's not true in general that if you take a complex number A, and multiply by the the conjugate of a complex number b star, this will give you a real number. Okay. And this is what we call the square of the absolute value of the complex number w. Okay. So this is the norm, or the absolute value, squared of this complex number w. So when I write here that just a second, that a state vector must be such that the absolute value of C1 squared plus the absolute value squared of C2 must be 1. I'm saying that you have to compute here C1 times C1 star, C2 times C2 star, and these must be equal to 1. So be careful with that. Okay. Okay. And there is a very important identity in complex analysis that we're going to use a lot. So I want to remind you. And this, the relations goes as follows. So if you have the exponential of I times theta, then this must be equal to cosine of theta plus I sine of theta. This is highly non-trivial, okay? So the identity that cosine, if you take this is a complex number, so if you take cosine as A plus I and sine you take as B, you're saying that if you have a complex number that can be written in this form as the cosine of an angle plus I times the sine of an angle, this is nothing but the exponential of I theta. And in order to prove that this is true, you have to work a bit with the expansion of the exponential here. But this is extremely non-trivial, okay? But this is a beautiful identity that you're going to use a lot. So this representation of a complex number as a cosine of an angle plus I sine of an angle, and then being equal to an exponential, has very nice properties. Namely, if I ask you what is the complex conjugate of this number, e to the I theta, you take the complex conjugate of this number, well, you just use the identity, and this will be, you take the real part of the number and repeat it. So cosine of theta appears with cosine of theta, and I sine of theta, then the complex conjugate is such that you change the sign of the imaginary part. So this will be minus I sine of theta. But the cosine has the property that cosine of theta is the same as the cosine of minus theta, so I can just replace cosine of theta by cosine of minus theta. And minus sine of theta is the same as plus sine of minus theta. So I'm just using trigonometric identities to write, to go from the left to the right of this equation. And then I look at this form and recognize that actually, if I use this identity here, this could be represented by e minus I theta. Now, if I take the argument of the exponential as being minus I theta and use this identity, I recover this number. So in summary, the complex conjugate of e to the I theta is e to the minus I theta, okay? And the second property is the following. If I want to compute the norm squared of e to the I theta, by definition, this is the number times its complex conjugate. So I repeat the number, e to the I theta, and multiply by its complex conjugate, which is e to the minus I theta. And using the properties of the exponential, this will be e to the 0, which is 1. Okay, so the norm squared of a complex number that is written as the exponential of I theta is 1. So those numbers that you can represent as exponential of I theta, they have norm squared being 1, and therefore we call that a phase. Okay, this has an interpretation if you want to deal with oscillatory mechanics or waves and so on. This represents a phase. Okay, but this is just a name. Okay, so this is, we call it a phase. But look, I can write any complex number. So I can have a complex number z as being the norm of the complex number. So if I write z as being the norm of the complex number, well, maybe it's better if I just write it as the norm of z times e to the I theta. Okay? You see that if I take the norm of z, then this is 1, so the norm will be well, would be the norm of z. And you see that I'm just decomposing the complex number in its norm times a phase. So this is another way of seeing complex numbers. They are a norm. So this is essentially the magnitude of the complex number, if you wish, times a phase. Okay? And of course, if we're talking about a complex number that has norm 1, then you can write the complex number as being, so if you have a complex number with norm 1, then you can write the complex number simply as a phase. Okay? Good. Okay, so I hope that this short recap puts everybody on the same page. Okay, and if you have troubles with complex number algebra, let me know so that we can discuss and that answer questions and so on. But now let me go back to the brass and cats. Okay, and now let's assume that we have a cat C with entries C1 and C2. Okay, so if I take the scalar product between the bra C and the cat C, this will give to me, so remember, in order to write down the bra associated to the cat C, I have to transpose the vector and take the complex conjugate. Okay, so the complex conjugate of C will be row vector C1 star C2 star, and the cat is just the column C1 C2. Now, if I take the product between C1 star with C1, by definition, as we just recapped here in the complex number recap, C1 star times C1 is the norm squared of C1. Okay? And C2 star times C2 is the norm of C2 squared. Okay? So if I take the scalar product of a state vector with itself, I get that the result is the norm squared of each component, and then you sum over them. Okay? But we have seen that state vectors must be normalized. So if they must be normalized, then the sum of this number plus the sum of this number must be equal to 1. So this is always true when you write a state vector, that if you don't know anything about the state vector, you know the only thing that you can ensure is that if you take the entries of this vector, compute the norm squared of each component and sum them, this must be equal to 1. So you automatically put a constraint on the entries of your vector, okay? Because if you choose C1 to be something, C2 cannot be completely random. It must satisfy the normalization condition, okay? So with that being said, okay, I will write a postulate, which I will call postulate 1 of quantum mechanics. So you have to be a bit careful here, because I'm saying now that I will write a postulate. So a postulate is something that it's a rule that I'm telling you that you should obey. And quantum mechanics is written in terms of postulates that you have to obey in order to describe the system, the physical system, in a precise way. So you can ask, but what is the justification for that? And is there a more fundamental explanation for this postulate? Well, those are questions that belong to a very important research area that is active. So you can, if you want to become researchers and if you want to do research in this field, there is a research field called quantum foundations. So people are still dealing with that. And this is an extremely active research field that people try to understand what are the very foundations of quantum mechanics. But look, there is a difference between having a theory that I know how to operate with, that I know how to extract physical quantities out of that, and the associated problems, which are why the rules are what they are. Okay? You see, these are two different level of questions, right? So one is, how do I extract physics? So I can give you a set of rules, and if you follow those rules, you are going to extract physical properties of a system, and you can be very happy with that and just apply the theory in order to extract physical predictions. Or you can sit, well, you can do both, of course, but you can sit on the other side and say, well, I want to understand why the rules are those. And, well, you might, spend an entire lifetime trying to understand why the rules must be those rules. But of course, I mean, you must have a starting point, right? You must have a point where you say, well, I have to fix a rule in order to derive different things. And many people want to write theories with the least number of assumptions that you have to make in order for the theory to work. So what I'm saying here is, I'm making this speech before that because we are going to write down postulates, and some postulates will simply not resonate with your intuition. And as we discussed previously, you don't have to expect that your intuition is something useful in the microscopic world, okay? Because you don't, I mean, you are not a microscopic being. So you have to take the postulates, trust them in the sense that, well, these are postulates that were tested over and over by several different experiments for about 100 years. And they seem to give the correct answers. So unless some experiment contradicts the postulates, namely, if you follow the postulates, then you don't get the right answer, the right prediction, then this is how physics work. I mean, you just write a set of laws, a set of rules, make predictions, and compare with nature. Okay? So I think, yeah, so I think I will stop for the break, and then we restart immediately with the postulate one, and we are going to start developing the rules that you have to follow in quantum mechanics in order to extract physics out of that. Okay? So, yeah, so we continue in 10 minutes from now. So see you in a bit.